sa présentation Piece of Cake.
Hello, we are students in the 7th grade at Costachii Negruții National College in Iași, Romania. Our teacher is Adrian Zanoschi, and this problem was proposed by him. Our names are Istrate Ilinca, Albert Matei, Damoc Andrei Răzvan, Lăpușteanu Alexandra, Oprea Alex Florin, Risescu Andreea Elena, and Ana Tudora. Our problem is called Piece of Cake. The first point is the presentation of the research topic. Problems of cutting a 2D shape, usually a cake, in multiple pieces of equal areas often occur in daily life. Although the approximation by eye is faster, it is not always accurate. In this paper, we are presenting multiple methods of cutting various 2D shapes in 2 or even more pieces of equal area. We are also going to present a method for cutting some shapes with holes in them, with the cake as well as the hole in it having some particular shapes. The second point is the brief presentation of the conjectures and the results obtained. A bakery produces cakes of various shapes. The height of the cakes can be ignored, and thus, the cakes can be considered plain geometric shapes. The shapes include circles, regular pentagons, various triangles and quadrilaterals, but the bakery also takes custom orders for other shapes. Study how the bakery can use as few straight line cuts as possible to cut the cakes into 2 pieces of equal area. What if the bakery now needs to cut the cakes into 3 or more pieces of equal area? Now the solution. The first case. The piece of cake has the shape of a triangle. Theorem. A median of a triangle, cake of course, splits the triangle into other triangles of equal area. We will have triangle ABC. M is the middle point of BC, and AD is perpendicular to BC. The area of triangle ABM equals to AD times BM divided by 2, and the area of triangle AMC equals to AD times MC divided by 2. And because BM equals to MC, the area of triangle ABM will be equal to the area of triangle AMC. Thus, by cutting the cake through AM, we will have 2 pieces of equal areas.
However, the middle is not the only line that satisfies our needs, as is in the following. Let ABC be a triangle and AD its altitude with D on BC. Next, we'll draw the right isosceles triangle AFD with AD its hypotenuse. Have AF is equal to DF, that is equal to AD over square root of 2. Now, let G be the intersection of the circle with center in A and radius AF with the altitude. Let I and J be the intersections of the parallel through G to BC with AB and AC. Because triangles IAJ and ABC are similar, it follows that the area of AJ over the area of ABC is equal to AG over AD squared, that is equal to AF over AD squared, that is equal to 1 over square root of 2 squared, that is equal to 1 over 2. Case 2. The piece of cake has the shape of a convex quadrilateral. Let ABCD be a convex quadrilateral. We are going to convert this case to the previous one. In order to do this, we'll draw the parallel DE to AC with E on AB. Because triangles EAC and CDA have the common side AC and the altitudes corresponding to it of equal length, we can deduce that their areas are equal. So the area of ABCD is equal to the area of ABC plus the area of ABC, that is equal to the area of ABC plus the area of EAC, that is equal to the area of BC. Now, if median CM has M on the segment AB, then our problem is solved because the area of BMC is equal to half of the area of BC, that's equal to half of the area of the quadrilateral. However, if median CM has its endpoint M outside of the segment AB, then CM will intersect AD in the interior point T, and the area of ABCT will be less than the area of BCM, that is half of the area of BCE, that is half of the area of the quadrilateral. So, in this situation, the line CT or CM does not solve our problem.
Now, I will show you how we can solve the problem of adding any convex quadrilateral shaped cake in two pieces of equal area using the result presented by my colleague Andrei. So whatever convex quadrilateral ABCD is, one of the triangles separated by diagonal AC, namely ABC or ADC, has an area greater than or equal to the area of the other one. If triangles ABC and ADC have equal areas, then diagonal AC splits the cake into pieces of equal area, so AC is the solution to our problem in this case. If the triangle ABC has its area greater than the area of the triangle ADC, we deduce that the area of the triangle ABC is greater than half of the area of the cake. So M, the midpoint of side EB from the previous construction, is for sure on side AB. Using the method presented by my colleague, we deduce that line CM divides the cake into pieces of equal areas. So line CM is the solution in this case. If the area of the triangle ADC is greater than the area of the triangle ABC, we deduce that half of the area of the cake is less than the area of the triangle ABC. We will solve the problem in the following way. As shown in figure 5, we draw BF parallel to diagonal AC, point F lying on line AD, and let M be the midpoint of side DF. Because AC is parallel to BF, we deduce that the area of triangle ABC is equal to the area of the triangle ACF. So the area of the quadrilateral ABCD is equal to the area of the triangle CDF. In the triangle CDF, CM is median, so it splits the triangle into shapes having equal areas. Using the two results obtained, we deduce that the area of the triangle DMC is less than the area of the triangle ADC. So point M lies for sure on side AD of the quadrilateral ABCD, and line CM is the solution to our problem in this case.
Now we consider the case when our piece of cake has the shape of a parallelogram. We need to prove that any line that passes through the intersection of the diagonals splits the parallelogram into shapes of equal areas. In figure 6, we have ABCD, a parallelogram. O is the intersection between AC and BD. EF is the line that passes through O. And CM is a perpendicular on AB. The area of BEFC is equal to CM times BE plus CF divided by 2. And that also equals to CM times DF plus AE divided by 2. And that equals to the area of DEFA. So if the area of BEFC is equal to the area of DEFA, then line EF splits the parallelogram into shapes of equal areas. Moving on to the next case, we consider that our piece of cake has the shape of a convex pentagon. In figure 7, we have ABCDE, an arbitrary convex pentagon. One of the triangles ABC or ADE must have an area which is less than a half of the area of the piece of cake. Now we presume without loss of generality that this triangle is ABC. We draw a parallel to AC through B, and that parallel intersects line CD in point F. Now the area of ABC is less than a half of the area of ABCDE, and the area of ABC is equal to the area of AFC. Now the area of AEDF will be equal to the area of AEDC plus the area of AFC, and that equals to the area of AEDC plus the area of ABC, which is the area of the piece of cake. The area of AFC is equal to the area of ABC, and the area of ABC is less than a half of the area of ABCDE, which is a half of the area of AEDF, so we can use the same method as the one we used in the previous case.
Case 4. The cake has the shape of a convex hexagon. Let A, B, C, D, E, F be an arbitrary convex hexagon. One of the triangles, ABC or AFE, must have a smaller area than half of the area of the hexagon. Let's presume that this triangle is ABC. That means that the area of ABC is smaller than half of the area of ABCDEF. Let G be the intersection of the parallel to AC through B and side CD. Therefore, now the area of triangle ABC becomes the area of the triangle AGC, and the area of the pentagon AFEDG is equal to the area of AFEDC plus the area of AGC, that is equal to the area of AFEDC plus the area of ABC, and that is equal to the area of the whole hexagon ABCDEF. Using the method from the fourth case, we will split pentagon AFEDG into two pieces of equal areas, cutting along a line AM with M on one of the sides CD, DE, or FE. It is certain that point M does not lie on GC because the area of AGC equals to the area of ABC, which is smaller than the area of ABCDEF, that is equal to which is smaller than half of the area of ABCDF, that is equal to half of the area of AFEDG. Therefore, line AM splits the hexagon into pieces of equal areas. The method applied to cases 1 through 4 can be used furthermore for convex polygons with 7, 8, 9 or more sides. We can also consider a situation when the cake has a hole in it. Theorem: in a circle, any diameter of the circle, which is a line that passes through the center, splits the cake into pieces of equal area. Case A, the cake and the hole are circle-shaped. Let O be the center of the larger circle and let Q be the center of the hole, as shown in figure 10. We will try to split both circles into two pieces of equal area. According to what we previously stated, when we discussed the case of splitting the circle, any line that passes through the center of the circle split it into two pieces of equal area. Therefore, a line that passes through O and Q will split the cake into pieces of equal areas. If O and Q are the same, figure 11, then any line that passes through this point satisfies the conditions of the problem.
Circle-shaped and the hole in it is paragram-shaped. So let O be the center of the circle, representing the shape of the paragram of the cake, and let paragram ABCD be the hole in the cake. So let's consider Q be the center of ABCD, and by using the result from splitting a paragram-shaped cake, we will deduce that any line passing through Q will split the paragram into two pieces of equal areas. So for splitting the circle, we just need a line that goes through O. And for splitting the cake, we'll just need a line that goes through O and Q, which is possible. And now we have the other case where O and Q are the same, so we only need a diameter for the circle to split the whole cake into two pieces of equal areas, which solves the problem in this case. So now case C, where the cake is paragram-shaped and the hole in it is circle-shaped. So let O be the center of the hole and ABCD be the shape of the cake, and Q be the center of ABCD. So using the same technique from the previous case, we will deduce that any line passing through O and Q will split the cake into two pieces of equal areas. And in the figure, as we see in figure 15, we have O and Q being the same. So we'll just need a line that goes to Q to split the cake into two pieces of equal area. So now we've gotten to case D, where the cake and the hole both have the shape of a paragram. So let ABCD be the shape of the cake and EFGH be the shape of the hole in it. So considering O and Q the centers of both of the two paragrams, according to the results from the two previous cases, we'll just need a line that goes to O and Q to split the cake into two pieces of equal areas. So now we've gotten to the second sub case where O and Q are the same, so we just need a line that passes through O. And this solves the case.
We will now present a calculation method for cutting a convex heptagon in three pieces of equal areas. This method can be also used for cutting in three pieces of equal area any convex pentagon with n greater than or equal to 3. First, let's consider O, A1, A2, A3, A4, A5, A6, an arbitrary convex heptagon. Using Heron's formula, namely S equals square root of P times P minus A times P minus B times P minus C, where S is the area of any triangle, P is the semiperimeter, and A, B, C respectively are the lengths of the sides of the triangle, we can compute the area of each of the triangles OA1, A2, OA2, A3, and so on. Adding them, we will find the area of the entire heptagon. Now, we will try and find x such that adding the area of triangles OA1, A2, OA2, A3, and so on until OAX, AX plus 1, we will get a total area of less than a third of the area of the heptagon. But adding the area of the triangle OAX plus 1, AX plus 2 to this area too, we will get an area that is greater than a third of the area of the heptagon. Therefore, we can find the point M in segment x plus 1, x plus 2, such that adding the area of triangle OX plus 1, M to this sum, we will get an area that is equal to 1/3 of the area of the heptagon. How are we going to find point M? In the following way. We know that the ratio of the lengths of the segments AX plus 1, M and AX plus 1, AX plus 2 is equal to the ratio of the areas of the triangles OAX plus 1, M and OAX plus 1, AX plus 2. We know both these areas and also the length of the segment AX plus 1, AX plus 2, so we can find the length of the segment AX plus 1, M, and therefore the position of point M. Working the same way, but from OA6, A5 this way, we can find another point N with the same properties. Therefore, lines OM and ON are the solution to our problem. This method can also be generalized for dividing a convex pentagon with n greater than or equal to 3 in m pieces of equal areas with m greater than or equal to 2 using m minus 1 lines. Now, the fourth point of our presentation, the conclusion. We have used both the calculation method and geometry to find ways of cutting different shapes in two or more pieces of equal areas, and we have analyzed some particular cases in which the shapes have holes in them. An interesting study would be to see how the problem can be solved if the height of the cake is taken into consideration. Thank you for paying attention.
Thank you very much, Iași, for this presentation. Is there a question among the public? Did you use GeoGebra to make some conjecture, some experience, or did you have you built a formal proof about all your errors calculations or your formulas?
We did directly the formulas on paper.
Directly formulas. Okay. Thank you very much. Thanks again.